Am I clearly audible to you all?
Yes, sir.
Okay. So in the last two classes, what we have taken your MCH 002 paper. In the last two classes, we have discussed three units of your paper. That is the separation techniques and different separation methods with solvent extraction methods. And today we will go in the next unit, that is your chromatographic technique. This is very much a well-known separation method widely used all over the world, and to separate the different constituents from a mixture. So I am just sharing my screen with you now. Is it visible, students? Anyone? Please reply.
Yes, sir.
Yes, sir.
Okay, 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 okay. So I welcome you all to this online class organized by RC Bhubaneswar. This is the unit 4 of your paper MCH 002, and this unit is all about basics of chromatographic techniques. So this picture is a picture of a mass spectrometer. It was invented by J.J. Thomson more than 100 years after the first mass spectrometer was invented. So, as per J.J. Thomson, he placed a very important line. That is, I feel sure that there are many problems in chemistry which could be solved with far greater ease by this than by any other methods. That means nowadays this mass spectrometer is equipped with gas chromatography. So this is in short, it is known as GCMS. That means gas chromatography mass spectroscopy, GCMS, which is sent with the satellites. Like our recently our Chandrayaan 3 was sent to the moon, and it is on the way to the moon mission. And in satellites mostly, GCMS was sent to moon or Mars to get different information or data from the surfaces. So this is just a pictorial diagram of your mass spectrometer, which is now equipped with gas chromatography uh, to have the GCMS apparatus. And we will not go through these things because this is related to your mass spectrometer. Okay, this slide, the chromatography. The chromatography technique was discovered by it's a Russian botanist named Mikhail Sweat, and in 1906 uh, he was working on chlorophyll and its experiment, and he concluded that so the constituents are separate with colorful components of the plant extract, and he called the new technique chromatography, where chroma means color and graphy means right. Okay. So he because the result of the analysis was written in color along with the length of the adsorbent column. So chromatography is basically the separation of the component on the basis of different properties of the constituent with the surface of the adsorbent if it is based on the adsorption concept. So almost after 1935, Adam and Holmes observe ion exchange character of the components. This is known as ion exchange chromatography, and likewise we have size specific chromatographies. So different chromatographies are there. One by one we will discuss. So the analytical scientists all around the world got actively engaged in improving the participating phases, detectors, and instrumentation, which is known as gel filtration chromatography, to separate the high and low molecular weight substances originated at Biochemical Institute in Sweden. And subsequently, we have the definition that chromatography is a method of separation in which the components to be separated are distributed between two phases, right? Distributed between two phases. One of these is called stationary phase and the other is known as mobile phase. And in the last class, we have already have shown the example and the mechanism of your chromatography where there are two phases. One is the stationary phase. It is generally your solid or liquid medium, and another is the mobile phase. It may be liquid or gas. So there are two phases. This is very important. One is stationary phase, and other is mobile phase. And in the previous class, we have this separation technique. We have this one. Wait. Yes, this one. This is the chromatography technique. Where this is the stationary phase and there is a mobile phase also. And when the sample is injected, what happens? Sample is injected now and it will move along this column, and with the interaction with the stationary phase, different components are gradually separated and giving the separated part of the mixture. Okay, so we have two components, that is stationary phase and mobile phase. Then historical development in chromatography. The first one, that is Way and Thomson in 1848, recognized the phenomenon of ion exchange in solids. Runge and these scientists 1850 to 1900 studied capillary analysis on paper. Lemberg 1876 illustrated the reversibility and stoichiometry of ion exchange in aluminum silicate minerals, and it is followed by this Sweat. In 1903 to 6, he invented chromatography with the use of pure solvent to develop the chromatogram. Chromatogram is the chamber in which the chromatography phenomenon occurs. Devised nomenclature used mild adsorbent to resolve chloroplast pigment. So, the chromatography which was invented by Sweat in 1903 to 6 was based on adsorption chromatography or adsorption phenomenon, where there is a adsorbate surface on which there is a adsorbent surface on which the adsorbate particles are gets adsorbed, and depending upon their interaction with the adsorbent, the adsorbent got separated. So in 1930 to 32, that is used activated lime, alumina, magnesia absorbent. Then we have again Homan Adams and synthesized synthetic organic ion exchange resin. Then Richtén in 1938 introduced the liquid or flowing chromatogram, thus extended application of chromatography to colorless substances, which was followed by Izamalov in 1938 discussed the use of TLC or thin layer of unbound alumina sprayed on glass plate, followed by Brown in 1939, first use of circular paper chromatography. But what we have used now, that is the thin layer chromatography. Okay, and there is also paper chromatography we'll discuss later, and it is Tiselius 1942-43 devised frontal analysis and method of displacement development. And again, these things invented or discovered one by one. That is the column partition chromatography by Martin and Singe in 1941. Then again, Constantine Martin 1944 first described paper partition chromatography. Then Boyd 1947-1950 ion exchange chromatography applied to various analytical problems. Then Lederer and Lindstedt 1948 applied paper chromatography to inorganic compounds. Kirchner 1951, it is TLC that we have practiced today. This is very popular and widely used method for the basic separation of the components. Then we have James and Martin 1952 developed gas chromatography, that is GC, which is equipped with the MS mass spectrometer to have GCMS. Then we have Sober and Peterson 1956 prepared fast ion exchange celluloses, followed by Lathe in 1956 used natural and modified starch molecular sieve for molecular weight estimation. Porath and Floty 1959 introduces cross-linked dextran for molecular sieving, and the last one will be Moore in 1964 gel permeation chromatography. We will have this unit also develop as a practical method. So, uh, chromatography, the stationary and the liquid phase, on these two phases, the whole chromatography mechanism depends. The stationary liquid, if it is the stationary phase is liquid, then stationary liquid is held on the inert solid support or coated on the wall of the capillary. The solid, whether it is support or an active material, is held in the form of column, then it is known as column chromatography. Then what are the importance of chromatographic method? The chromatography has application in every branch of physical and biological sciences, and 12 Nobel Prizes was awarded between 1937 to 1972 along the work in chromatography. And then these are the simple definitions of your chromatography. As I already told you, the substance in a mixture are not chemically combined, so therefore they can be separated through some physical processes. So chromatography, a technique for separating the components or solute of a mixture on the basis of the relative amount of each solute distributed between a moving fluid stream, which is moving, which is known as mobile phase, and a contiguous stationary phase. The mobile phase may either liquid or gas, and stationary phase is either solid or liquid. And the chromatography is the ability to separate molecules using partitioning characteristic of molecule to remain in a stationary phase versus a mobile phase. Once a molecule is separated from the mixture, it can be isolated and quantified. So they are very much fundamental. So different chromatographic techniques. So depending upon the stationary and mobile phase, we have different type of chromatographic techniques. Likewise, we have the stationary phase and mobile phase. Stationary phase, if this is solid, then we have thin layer chromatography. Second was paper chromatography and column chromatography. In column chromatography, silica gels are generally used to separate the constituents. And the depending upon the mobile phase, we have liquid chromatography and gas chromatography. Classification according to force of separation, that is which type of force is is applied or is there between the mobile phase, stationary phase, and the solute component in the mixture. We have different type of forces of separation, that is adsorption, where there is adsorbent surface which gets adsorbed by adsorbate molecules or particles. We have partition chromatography where partition occurs, then ion exchange where cation and anion will exchange, then gel filtration, then the last one is the affinity or the interaction chromatography. So before going to this part, that is thin layer chromatography, let's have the PDF that we have from the IGNO. So the definition part already okay. So this is depending upon the shape of the solid support, that is the stationary phase, the classification, the nature of the mobile phase. This is another category, and the mechanism responsible for separation. This is a force of separation. Okay. So we have adsorption, ion exchange, partition, then we have gel, then affinity. So we have generally 4 to 5 types under this mechanism responsible for separation. Then according to solid support, we have paper chromatography, thin layer chromatography, and on the basis of mobile phase, we have like this. We have liquid chromatography and gas chromatography. Okay, so okay, then let's have this one. Now, for summing up the classification of chromatographic techniques, it emerges that there will be 3 types of chromatography techniques, that is liquid chromatography, gas chromatography, and supercritical fluid chromatography. So, in liquid chromatography, the simplest one with liquid as a mobile phase seems to be based on partition between liquids supported on an inert support and other liquid acts as mobile phase. So there are two liquids used in liquid chromatography. One liquid is your solid phase and second one is your mobile phase. This is also known as liquid partition chromatography, where the mechanism of partition or force of separation which is acted is in the form of partition. The support holding the liquid can be in the form of 3 dimension, that is column, or 2 dimension thin layer or paper. So the chromatography like thin layer chromatography or paper chromatography, as we have discussed yesterday, like this one, like this one. Yes, this one. This is just a paper chromatography where paper is used as a two-dimensional mechanism, where this paper is equally divided with 3 parts, and there are three identification marks are here, and I have put 3 samples like this. One is your reactant, second one is your product, and third is the reaction mixture where both reactant and product both are there. Then this is a two-dimensional scenario, and we have 3 samples again, and when it is dipped in the ether or hexane solution, the constituent are separated based on their adsorption to the paper. So this is the TLC. Okay. So then thin layer and paper. Okay. Then we have descending and ascending chromatography like your TLC or column chromatography. These are all. Then we have normal phase chromatography. Uh, then just go through these things, the same things are written. Then another is there liquid solid chromatography. That means here the solid is the solid stationary phase, liquid is the mobile phase, and this is known as liquid solid or solid liquid chromatography. Then we have this one ion exchanger, where cation and anions are get exchanged If cation is exchange, this is cation exchanger, and if anion is exchange, anion exchanger. There are amphoteric exchanges which are capable of both cation and anion exchange. Ion exchange, with a very few exceptions, is a reversible process. As I already told you in the last class, this ion exchange phenomenon must be irreversible. Okay, so these are very much irreversible processes. Every ion moved from the solution is replaced by an equivalent amount of another ion. Ion species of the same sign. There is another form of chromatography which is synonymous to ion exchange chromatography and is known as ion pair chromatography. Okay, just go through these things. These are very, very fundamental. Then one by one we will discuss. Then gas chromatography part, we have GSC and GLC. But this gas liquid chromatography, this is very popularly used, GLC. So in gas chromatography, the mobile phase is gas, and if the stationary phase is solid, this is known as gas solid chromatography, and if the mm mobile phase is liquid, this is known as GLC. That is the gas liquid chromatography. And in GSC, the retention of the analyte is due to physical adsorption on the column material. So and in GLC, separation taken because of partition between gaseous mobile phase and liquid immobilized on the surface of inert solid. GSC is not as popular as GLC. As I already told you, GLC is very much popular method which is frequently used to separate the constituents. Then supercritical fluid chromatography. So during we have there are one thing, that is the critical temperature and critical pressure. Okay, so during the last quarter of the 12th century, another type of chromatography with an entirely new type of mobile phase, that is supercritical fluid, has come up on the forefront. It is basically partition chromatography. Here, instead of liquid or gas, we use a supercritical fluid. In order to understand a supercritical fluid, we will have to know critical temperature and critical pressure. The critical temperature of a substance is the temperature above which a distinct liquid phase cannot exist regardless of the pressure. So this is known as critical temperature. That above this temperature, the liquid phase cannot exist. The vapor pressure of the substance at its critical temperature is known as critical pressure. So vapor pressure is equal to your escaping tendency. So the liquid phase or the liquid gets vaporized at what temperature, and that temperature is known as critical temperature, and the vapor pressure is known as critical pressure. At temperature and pressure above its critical temperature and pressure, a substance is known as supercritical fluid. So, if we use this type of fluid, supercritical fluid, as the mobile phase, then this chromatography is known as superfluid chromatography. This is not very much important to you because another methods which you have there in your different units, and you will face different questions from your theory paper from that part. Okay, so this is very important. That is the this table. Just see this table. We have a classification of chromatographic methods, general category, stationary phase, mechanism, and mode. General category, we have LC, that is the liquid chromatography. So where the mobile phase is the liquid, and the stationary phase, it may be solid or organic bonded to solid surfaces. Mechanism is partition chromatography, and the mode will be column or two-dimensional, means paper or TLC, then reverse phase, etc., etc. This ion pair formation also one type. Then under this, that is LC, if the stationary phase is solid adsorbent, then we have adsorption phenomenon, and the mode will be column and two-dimensional. Then third type, If it is liquid chromatography, but the stationary phase is ion exchange a liquid in interstitials of a gel. We have we used a gel-like structure, gel-like substance where ion exchange occurs. Then we have ion exchange partition, also known as sieving, column, two-dimensional batch, etc. Then we have GC, gas chromatography, where the mobile phase is gas and the stationary phase is solid adsorbent or liquid adsorbent. Then we have partition and the mode is column. Then for solid, it is adsorption and the mode is column. Then similarly, the supercritical fluid chromatography, we will use the SFC or supercritical fluid as mobile phase, and the solid phase, the organic species bonded, there will be partition and column. Okay, so just try to remember this table, and we will you will have a good conceptual clarification on chromatography by this table. The illusion of column. Illusion of column is this one. This is known as illusion of column. ELC we have. Wait. So this step is known as illusion of column. Just see, this is known as that the constituents are separated on the basis of their adsorption or interaction with the chromatogram. Okay, so this is just a column chromatography picture, and that was the TLC, thin layer chromatography or paper chromatography. This is just a column, okay, which is sealed with silica gel, and the compound is made a slurry. We prepare a slurry with the silica gel and the compound. Then this was mm, gets separated by using different percentage of ether and hexane. So first the ether is used, then it was percentage 1%, 2%, 5%. The solvent is added to separate the constituents. Okay, so we will have a different concentration profile. Then we have one component moves at a faster pace and other at a slower rate. The rate of zone broadening of the two species decrease. So this depends on the rate of the movement, the movement of the constituents in the column. Then we have some mathematical things are there in our chromatography. The migration rates or the kinetics we will study. The distribution constant. Let in chromatography, the distribution equilibrium is between mobile phase and the stationary phase. That is, X solute is equilibrium with X stationary or stationary phase. The equilibrium constant K is will be the equilibrium constant K for this reaction is known as distribution constant, which is equal to K equal to Cs by Cm, where Cs is the concentration of the stationary phase and Cm is the concentration of the mobile phase. Okay, then we have retention time. Retention time means how or the time of retention of the constituents in the column or chromatography. In the preceding subsection, we have introduced a term known as retention time. It is time taken after sample injection for the analyte peak to reach the detector. That means when the sample is injected and when the time at which we will have the detector response, that is, we will get the result. The time gap between these two is known as retention time. That means the sample is retained. That means the sample is retained on this on the chromatogram is known as the retention time. That is from the time of injection of the sample to the chromatogram and the and at what time the detector is responded, that is known as your retention time. So we have there is a peak, that is the detector signal and versus time. So the small peak in the at the beginning on the left is for the species that is not retained at the column. So this will be a small peak that it will not retained in the in the column. So this is the small peak, and where there is a broad peak, that means the retention time is considerable, and this is your the next peak. This peak is your for the where the retention time is more than the first peak. Then we have, if if L is the length of the column, the average rate of migration of solute molecule is given by the following expression. So we have V is equal to L by TR. Similarly, the average linear rate will be U equal to L by Tm, the length of the column divided by time, Tm. So then we have these things where Tm is the dead time and Lr is the retention time. Tr is the retention time. So it is the time required for the average of the molecule of the mobile phase. Average of the molecule of the mobile phase. Just wait. Just
Sir, I think you are on mute.
okay. Thank you. So just go to back. Then we have this equation, that is V equal to L by TR. Okay, and we have similarly the average linear rate of the migration mobile phase U equal to L by Tm. This is the average rate of migration V equal to total length of the column divided by retention time. This is average rate of migration, and if we calculate the average rate of migration in the mobile phase, then it will be U equal to length of the column divided by time taken for mobile phase, or this is the dead time, Tm. So the total average migration of the V equal to U into fraction of time of the solute spent in the mobile phase. That means what time it is taken, or what fraction of time with respect to the total time is taken in the mobile phase. So the fraction of time, it is equal to moles of the solute in mobile phase divided by total mole. That means out of total mole means it is the concentration of the mobile phase plus concentration in the stationary phase, out of which only the mobile solute we will take. So that means mobile moles of the solute in the mobile phase will be concentration in mobile phase into volume in mobile phase divided by total mole. Total mole will be Cm in CmVm plus CSVs, because CmVm is your moles in mobile phase and CSVs is the moles in stationary phase. So that's why the equation again simplified, and it is equal to V equal to U into, if I divide this equation with CmVm, this will be 1 by 1 plus CSVs by CmVm. As we know, Cs by Cm equal to K, so that's why the this is the distribution constant, okay, K, or the equilibrium constant. So this equation 4.7 will be V equal to U into 1 by 1 plus K Vs by Vm, because Cs by Cm is your K. So this is the V, or the average migration time. Then the retention factor, retention time is there. The second one is the retention factor. Retention factor means it is a factor which depends on the retention of the constituent in at the column. This is retention factor. So there is another term known as retention factor, or capacity factor, which is commonly used to describe the migration rates of the solute, for solute. If the concentration of the solute is X, the retention factor Kx is expressed as small kx equal to capital Kx Vs by Vm. This is the volume of the volume in stationary phase divided by volume in mobile phase. That is a retention factor. Then we have, as we know, V equal to U into 1 by 1 plus Kx, because this factor Kx Vs by Vm, this one Kx Vs by Vm. Okay, so this factor was replaced by small kx. So we have V equal to U into 1 by 1 plus kx. This one. Okay. Now substituting L by TR equal to L by TM into 1 by this. We have rearranging. We have this one. Kx equal to TR by TM by TM. So this is the retention factor, and the previous was the retention time. Then which is followed by another mathematical expression, that is selectivity factor, or this is known as the separation factor. The relative migration rates of the solute are expressed in terms of selectivity factor. The selectivity factor, or select separation factor, alpha of a column for two solutes X and Y is expressed as alpha equal to Ky by Kx, where K is the distribution constant for Y and X is the distribution constant for your elute species X. So alpha equal to, the selectivity factor should always be greater than unity. So substituting these things, we have alpha equal to small ky by kx, and then the equation 4.14 can be converted in the form of retention time. That is again that one, this one. We have alpha equal to try by tm divided by trx by minus tm. Then again the shape of the peak. At this stage, it may be important to examine the peak of chromatogram. The bands on a column, just see 4.1 figure. They show a similar or normal error or Gaussian curve when the values of the, just go through these things. Okay, this is not very much difficult to you. Concept of theoretical plates. With all the concept learned up to this stage, we may be in a position to access the perform of a column. When we say performance, it automatically implies efficiency in attending a separation. The various factors contributing to efficiency are examined by a concept known as height equivalent to theoretical plates, HETP. So there is n equal to L by h, where n is the number of plates, h is the plate height, okay, and L is the length of the column. So that means when the separation occurs in a column chromatography, there is separation with height of the constituents. Just see these things. Just I am writing column chromatography. Just see these things. Here what happens, because but this is the stationary phase, this is a loaded sample green in green color, and this is a mobile phase, that is the solvent we have added ether or hexane or percentage of that. And on adding this solvent, that is a mobile phase, the sample gets separated. Okay, and it will get separated, and the loosely bound component will separated fast, followed by the that means the green is now have two components, green and orange. So orange have stronger interaction and green have less interaction. So which have less interaction, this will separate first, this will separate first, followed by the, so this the so the length of this component is known as the height, and the total length of this column is known as L, capital L, and this is the H of each component. Okay, so this is just highlighted here. This is L by H means N is the number of plates. So how many number of plates are here? There are two plates are here. So number of plates. Total length divided by length of each column. So this is your L by H. So we have just go through these things: time, peak height, sample injection, baseline, etc. We have a equation here: n equal to 16 PR by WB. So WB is a width. WB. It is the width means these things. Width means the breadth. It is the width. Then we have rate theory, that is a kinetic theory. If we have height divided by linear flow rate, we have these two things. Then these things are not required for your examination point of view, and this will not come. Generally the different principles and are required. I have just keep these things, non equilibrium not required. Then we have resolution. This is one important thing in your chromatography. The foregoing discussion on reducing the broadening of the peak is essential. Aim to achieve a minimum overlap between consecutive peaks of the analyte. In other words, the position of illusion band on a horizontal axis and their width will determine the extent of separation. The quantitative measurement of ability of column to separate two analyte is expressed in factor known as resolution. This is the quantitative measure of ability of a column to separate two analytes. This is a quantitative factor, okay, which is very much responsible to separate the analytes or constituents from their mixture, from their mixture. The factor is known as resolution factor. Then these are the equations. Let's try to remember these things. And W stands for width, T is the time of the retention, and we have again the alpha concept is again here. Okay, so this is all about your first unit. Then the important is your next unit, that is the unit 5. Yes, this is a liquid chromatography. Before going to this part, let us we have again the same PPT. We have a liquid chromatography means the mobile phase is a liquid. Mobile phase is liquid, and the stationary phase may be solid or liquid. If it is solid, then this will be your liquid solid column chromatography, and if it is liquid, it is your liquid chromatography. Liquid means both solid and both the stationary and mobile phase both are in liquid phase. So in the previous unit we go through classification general principle of chromatography. While classifying the different chromatographic techniques, the main criteria was the nature of mobile phase and the stationary phase. It was point out that a large number of classification are available based on the uh, liquid chromatography. These are mainly due to shape of the chromatogram or shape of the column, nature of support, and the mechanism. Mechanism means it is the force of separation. It may be adsorption, partition, ion exchange, or sieving, which are responsible for the separation. So, in liquid column chromatography, we normally use the we normally used two types of chromatography, that is liquid chromatography or liquid solid chromatography. So liquid solid chromatography is based on your adsorption phenomenon, that is the paper chromatography or TLC, like thin layer chromatography. And um, and we have we have also ion exchange and gel sieving chromatography. Thus, we will discuss only liquid solid chromatography (LSC) and liquid chromatography in this part. Okay. So, what are the thin layer chromatography? It is a method of your solid liquid chromatography. So, TLC, it is a method for identifying substances and testing the purity of the compound. TLC is a useful technique because it is relatively quick and require small quantity of materials. As already demonstrated you in the last class, the paper is required. Then you have to fold it through two equal sized slots. Then at the bottom you will put your samples and place it in a chromatogram containing ether hexane solvent. Then gradually, on the basis of its absorbent property, it will separate. So this technique is a very quick technique. It will require some fraction of a minute, and also small quantity of the material is needed for TLC. So separation in TLC involve distributing a mixture of two or more substance between stationary and mobile phase. There will be two or more substances which can be separated. The stationary phase is the adsorbent, generally silica gel as already mentioned, or it may be alumina, means aluminum oxide, coated on a plate. And the mobile phase is a developing liquid which travels of the stationary phase carrying the sample with it. That means the mobile phase is the solvent we have taken in the chromatogram or the chromatographic chamber. It is hexane or ether or mixture of both. Components of the sample will separate on the stationary phase according to how much they adsorb. Very important. How much they adsorb on the stationary phase. That is the paper, TLC paper, versus versus how much they dissolve in the mobile phase. That means the component is dissolved in the mobile phase and gets adsorbed on the solid phase. Okay. So this is a pictorial diagram of your thin layer chromatography where a TLC paper used. This is the paper. TLC paper is used here, and this is the origin. That means from the bottom at a certain height, one line is drawn, which is known as origin. This is the sorbent, the surface of the paper. This is TLC plate. This is the chromatogram or the glass tank, and this is the solvent we have used, generally ether or hexane, and there it should be covered with a lid. So this is the things or apparatus required for your TLC chromatography. Just see, this line is known as the origin. Okay, so though so this is the origin part that is just above your bottom line, and this at this origin, the different samples are placed with the help of capillary tube, and if we placed this paper in the chromatogram chamber and with the required solvent, we will have different components at different heights. But this is the thin layer chromatography. So identification of the spot. So these spots are not generally not visible to naked eye. These are seen under the UV lamp, ultraviolet lamp, or it if it is not visible in ultraviolet lamp, this may be visible in iodine solution. Iodine. Okay. So if the spot can be seen, outline them with a pencil, and spots are outlined. That it make we will make a circle around the spot with the pencil. If no spots are obvious, the most common visualization is under UV lamp. Many organic compound can be seen using this technique, and many commercially made plates often contain a substance which aid in the visualization of the compound. So this is the TLC chromatography, a thin layer chromatography, where the TLC paper is used, and the spots are seen under UV lamp generally. If it is not seen in naked eye, this will be seen under UV lamp, and it is also seen in iodine box. Then visualize, just see this one. If it is iodine, then the compound is aromatic compound. If it is UV lamp, it is unsaturated compound generally. P anisaldehyde, it is carbohydrate. It is a bromocresol green, it is carboxylic acid. If it is 2 for dinitrophenylhydrazine, it will mainly for aldehyde and ketones. If it is ninhydrin, then it is amines. If it is sulfonilic acid, then it is phenolic compound. Turn orange if it is diazotized or Pauli's reagent. Yellow with this reagent. Then if it is sulfuric acid, it is sprayed on the TLC. If the reagent is aniline phthalate, the compound may be sugar. If it is antimony trichloride, if it is antimony trichloride, then it is maybe glycoside. Then if it is Drazen drops reagent, just search it in online. It is alkaloid. Then how we can interpreting the data? It is interpreted using a factor known as retention factor. So what is retention factor? So retention factor means the length of retention of the component in a column or in a TLC. It is known as retention factor. So it is mathematically, it is distance covered by the analyte divided by distance covered by the solvent. That means just see this one. So this is the maximum height of the solvent, which is which the solvent is the distance covered by the solvent. This height. Okay, there are 4 samples, and we have the solvent at the bottom, and when I put this TLC in the chromatogram, the solvent will rise, and the total distance covered by the solvent is this one, this line. This is the total distance covered. Okay, then we have to measure the distance covered by each component. That means if I measure the distance covered by this red component, then this is the height covered, or this is the distance covered. So the retention factor will be the distance covered by the component divided by distance covered by the solvent. It is known as retention factor. So this is the retention factor for your red component, and similarly this brown component or yellow component or dark yellow component, this all have will be the same type. That is the distance covered by the individual component divided by the distance covered by the solvent. So this is known as retention factor. So retention factor value for each spot should be calculated. So for every component or every spot, the retention factor must be calculated. It is characteristic for any given compound on the same stationary phase using the same mobile phase for development of the plates. That means the different components are measure the distance of the different components measure with the same solvent, or that is the same mobile phase. Hence, known retention factor value can be compared to those of the unknown compound to aid their identification. So we have some standard data related to our retention factor of the unknown compounds. If we get the retention factor of the unknown substance, then we will match it with the known value, and from this we may predict what type of compound we have. Okay, so before going to this part, let's go to our PDF unit. Let's go to our PDF. So liquid chromatography. Then we have the objective of this unit are recapitulate some of the basic concept of liquid solid and liquid liquid chromatography, understand the functioning of the component of an improved version of a liquid chromatographic setup, appreciate the criteria used for choice of stationary and mobile phase, describe development technique used, get an idea about HPLC, that is high performance liquid chromatography, HPLC, and the last one is enumerate some of the important application of the column chromatography. Then we have liquid solid chromatography. This is the separation factor alpha. Then we have liquid liquid chromatography, experimental setup. This is the experimental setup. So this is the column, okay, which I have shown you. This one. This is the column. So to this column, we have taken generally silica gel or alumina as the stationary phase, and with the help of syringe, we put the sample here, and after putting the sample, we will add the solvent, the required solvent, with starting from 0%, 1%, 2%, 3%, etc. Okay, then we have then we have a mobile phase reservoir slurry device. Slurry device means the sample is converted to a slurry using the solid phase that we have taken. That may be your silica gel or alumina. So the number one is the mobile phase reservoir. Number two is the slurry device. Okay. Then number three, it is the lamp or heating device, which is generally not needed. Then number four is your pumping. Number five is your pressure monitoring device. This is pressure device. Number six is the pump. Seven is the filter. Eight is the pre-column. This is the pre-column. Nine is the column. 10 again is the pumping, that is from pre-column to column. 11 is the injection port. 12 is the column thermostat. 13 is the detector, and 14 is the recorder. So this is very much a instrumentation or mechanistic approach to your liquid chromatography. So what are the equipments? The mobile phase or reservoir. This is our first one. It holds 1 liter of the mobile phase. This reservoir is made up of stainless steel, which is inert to most mobile phases and is not subjected to breakage. Many different forms of reservoirs have been used, and simple units may be constructed from glass flask or bottle of an appropriate size. Some reservoir are designed so that the mobile phase may be decaged in situ. Decaging is required to eliminate dissolved gases, particularly oxygen. To permit in situ degazing, reservoirs are sometimes equipped with a heater, a steering mechanism, an inlet for applying vacuum, and a nitrogen purge. So this is the mobile phase reservoir where 1 liter capacity of the mobile phase is taken and made up of your stainless steel with a diesel to remove the dissolved oxygen. Then pumping. So one of the most important part of the modern liquid chromatography instrument is the pumping system. In liquid chromatography, the resistance to flow of the long, narrow column packed with small particles is relatively high and high pressure are required. Pumps are grouped in two categories: mechanical pump to deliver the mobile phase at a constant flow rate, and pneumatic pumps which deliver the mobile phase with a constant pressure. So if the flow rate is constant of the mobile phase, this is a mechanical pump, and if it is at constant pressure, then it is pneumatic pump. So two types of pumps are there. Then followed by a filter. A filter is normally placed in the line following the pump to remove fine particle of particulate matter which can clog the inlet of the column. Generally, a 2 micron sintered stainless filter is adequate for this purpose. That means to separate the large size solid, the large size stationary phase, the solid we have used to separate these things. We have to filter it with 2 micron sintered stainless steel filter. Then pressure monitoring device. A device for monitoring the column input pressure should be inserted in the line between the pump and the chromatographic column. This pressure monitoring device indicates if there has been a plugging of the column or failure of the pumping system. So this is just a monitoring device. This is the fourth one. This one. Okay. So this is just a pump monitoring device. This one. Number 5. Then a sample introduction device. So this device is very important factor in obtaining high column performance. The sample should be introduced as an infinitely narrow band on the chromatographic bed. The more diffuse is the plug of sample in the mobile phase introduced into the column, the wider is the separated column band at the end of the column. The sample is injected with a micro syringe through a septum containing in a low volume inlet system. Septum material is generally made up of silicone or neoprene. It is generally not feasible to make syringe injection above 50 psi through sampling ports. Therefore, at high pressure, a stop flow injection technique normally with the syringe. Just see what is septum. So this is the septum. It is used for to septum used in chromatography. Just see. This is just a rubber-like material, okay, which is used to close this column, and the syringe is used um, to inlet the sample into the column. So then the column, this is just made up of a glass cylindrical glass and the unpacked column must be constructed of a material that will withstand both pressure and chemical action in the mobile phase. Most columns are made up of stainless steel tubing. However, heavy walled glass columns are sometimes used at a pressure of 600 psi commercially available for these things. Just go through these things. This is just very common things. These are U-shaped. The length of the column should be 25 to 150 centimeter. Then we have column thermostat. It is important to control the column temperature in liquid chromatography. The temperature variation within the column should be maintained within plus or minus 0.2 degree centigrade. The large change in column temperature can result in significant variation in retention time. So the temperature is a vital factor which significantly affect the retention time of the uh, components in the column. Then finally the detector which detect in LC, the ideal detector should be high sensitivity, good precision, predictability response to all solutes. It should be unaffected by change in temperature and carrier flow. It should not contribute to extra column band broadening. It must be non-destructive of the solute. Two types of detector are used that depends on the bulk property or general detector and solute property or selective detector. So there are two types of detector, that is general detector, that is a bulk property, and solute property or selective detector. The bulk means it is not surface. This is the bulk. That means if I go to this one, if I go to this one, so this is the surface, and and under this these are all bulk. BULK, bulk. So there is bulk detector as well as solute detector or selective detector, which detect the solute or the selectively detect the solute. Then we have column packaging, and this will be packed with the silica gel or alumina. The packing of column is LC are described in terms of adsorbent or stationary phase, the type of particle and particle size. So we have to consider different parameters before packaging of a column. So the different parameters are what type of stationary phase we have to take, and what is the particle size, or what type of particle we will take. So these are the parameters we will think before packing a column. Each of these particles characteristics has an important effect on the performance and use of a given packaging material. The column are packed by various techniques such as dry packing of rigid solid material using tap fill procedure. Tap fill procedure means just you have to put, we have to put the packaging material through this mouth. Okay. So just in we do the column separation by using or the packing of the column by using a just a glass funnel, and put different particle size of silica gel to it. Just you have to put a funnel here. You have to put a funnel here, and by using this funnel, you have to put the silica gel of different particle size that you need. Then after this, there will be filling of this column with the silica gel. Okay, but this method is known as dry packaging. Then slurry packaging means you have to prepare a slurry. Okay, you have to prepare a slurry with the help of your sample and the silica gel. You have to put you have to take your sample in the given solvent, and you have to add some silica gel, and you have to prepare a slurry. Okay, and you also pack your column with that slurry packaging. And similarly, slurry sedimentation method for soft gels, and this is for your hard gels. So two types of, that is slurry packaging and slurry sedimentation, means it is for soft gels. You will take slurry sedimentation. So choice of stationary and mobile phase. This is another important part. That is your how to select uh, stationary and mobile phase in a particular chromatography. The success of separation by liquid column chromatography depends on the choice of stationary and mobile phase. In LSC, liquid separation chromatography, the stationary phase is an adsorbent. As the in LSC, the phenomenon or the force of separation is adsorption. So the stationary phase must be an adsorbent on which the components acts as adsorbate, which are gets adsorbed on the adsorbent. And once we talk about adsorbent, some of its properties like surface area, adsorbent type, particle size, and activation and regeneration become very important. That before selecting an adsorbent, we have to think, or we have the concept like what type of adsorbent we will take. The surface size depends on the particle size, and that if I take 60 micron silica gel, and if I take 120 micron silica gel, then 120 will have larger size. And if the size of the stationary phase or the adsorbent is more, then the pores will be larger. Okay, and if the size of the silica gel is less, then the pores will be very small. So in LLC, liquid chromatography, the stationary phase is a liquid immobilized on an inert support. While considering the liquid, its polarity and tendency to leach out become important. And these are the things. Then again, type of adsorbent. Various adsorbent type exist, like your polar adsorbent, like metal oxide, magnesium silicate, etc. Which are selectively adsorb unsaturated. Just remember this thing. You have to remember, because this will come in your examination. Now, what type of stationary phase is will be selected in liquid chromatography? You have to put this. You have to write these properties of the adsorbent. And this polar adsorbent will adsorb unsaturated aromatic and polar molecules like alcohol, amine, acid, etc. Polar adsorbent may be further divided into acidic, basic, and neutral on the basis of pH. Silica, magnesium silicates are acidic, and thus they chemisorb bases. So which are acidic adsorbent, they follow the mechanism or the theory of chemisorption. The alumina surface containing both acid and base, nonpolar adsorbent such as graphitized carbon, which is a strong adsorbent, and kisel gur, which is a weak adsorbent, so no selectivity for the adsorption of polar molecules. So neutral adsorbents will have lesser selectivity than your acidic and basic adsorbents. Then we have surface area, as already discussed, the surface area and pore diameter. This is very important. Pore diameter. If the surface area of the adsorbent is larger, pore diameter will be larger. If it is smaller, this will be smaller. So pore diameter of a given adsorbent vary widely with the method of manufacture. In adsorption chromatography, that is liquid chromatography, the separation depends on the transport of molecule through the system, on the interchange of the molecule between an adsorb phase and a liquid phase. If the volume of the adsorbed phase per unit quantity of the adsorbent is low, both the amount of the interchange between the phases and the amount of separation will be small. For this reason, when dealing with large sample, it is important to select an adsorbent with a large surface area. This is very much common that if we have a sample with a large size, that the molecular weight is very high, then what happen? We should select one adsorbent with large surface area. That is, we have to select 200 or 300 micron silica gel, not 60 micron silica gel, like this. Particle size. The effect of particle size of the adsorbent on the sharpness of chromatographic separation has been noted by many investigators. For sharp separation, it is recognized that a finely divided material is necessary. An adsorbent in the range of 100 to 200 mS, that is equivalent to 149 to 74 micron in particle size, is specified. This is the size of your particle of the adsorbent. That is, if it is 100 mS, that means it is 149 micron. If it is 200 mS, that means the pore size or the particle size reduces, that is 74 micron. However, it is more difficult to pack column uniformly if it is adsorbed is very fine. If the adsorbent is very finely divided, that is below 50 micron in particle size. Okay, so that means if it is 50 micron, the mesh will be the mesh size will be larger, so we will do not have a uniform packaging. Then some adsorbent are available only as finely divided powder with just hold. Hello, can so the particle size as well as the type of adsorbent and surface area of the adsorbent is important factors to select which type of adsorbent we have to select for our sample. Then we have activation and regeneration of adsorbent. The term activation means those processes which are used to enhance the effectiveness of an adsorbent by improving the pore structure and increasing the surface area. This is known as activation. And degeneration. So how effectively we will improve the pore structure all depends on this pore, that the size of the pore, that is a hole which create after the packaging by silica gel or alumina or any other hard or soft gels. In general, with carbon, high temperature activation produces an organophilic adsorbent. Organophilic means where organic materials gets attached, and low temperature activation a hydrophilic adsorbent. During adsorption, the pores of the adsorbent becomes filled with adsorptive molecules. The term regeneration refers to the term regeneration refers to the removal of the adsorbed molecule and the return of the adsorbent to its original state. The regeneration of the adsorbent can be carried out by gentle heating if the adsorbed molecule are volatile. If they are non-volatile, they may sometimes be removed by elution or desorption with volatile solvent. That means it is application of heat, which in turn may be removed by gentle heating. With some adsorbent overheating will destroy the pore structure. Example, silica gel should not be heated above 200 degrees centigrade. It will destroy the pore structure of the silica. On the other hand, rugged adsorbents, Fuller's earth and bauxite, that is bauxite is the alumina, Al2O3, may be heated in an oxidizing atmosphere to temperature coefficient to bond the adsorbed material near 540 degrees centigrade. Then we have stationary phase used in LLC, that is liquid liquid chromatography. And these things all about liquid solid chromatography. Okay, that is the paper or TLC, these are all liquid solid chromatography. Then we have liquid liquid means here the stationary phase is liquid and the solid phase is liquid, both these phases are liquid. So in liquid liquid column chromatography, the stationary phase is liquid, that is immobilized on an inert support. The stationary phase fall into two classes, the more usually hydrophilic one and reverse phases. The stationary or supported liquid phases have been of many kind of varying polarity from water to paraffin, and as a large number of liquid stationary phase can be held mechanically on an inert support. Such stationary phases have some disadvantages. These are the basic things. Then in liquid liquid column chromatography, there are four different techniques for preparing column coated packaging. So in liquid solid, we have directly put the silica gel or alumina, or we make a slurry of that sample and silica gel, and we pack the column. But in liquid liquid, there are four types of techniques are used for packaging. That is solvent evaporation technique, in situ coating procedure, the solvent filtration technique, the equilibration. The first one, supports for liquid liquid partition chromatography. It should be chemically inert and it must not dissolve or swell in the stationary phase. That the liquid which we will take for the stationary phase, it must be chemically inert. It cannot be, it should not be react with the mm the liquid phase we will take as mobile phase, and it must not be dissolve or swell in the solid phase. It should display good wettability by the stationary phase, and it should neither dissolve nor react with the mobile phase. This is also very important. It should consist of particle as identical as possible, which allow the most uniform and reproducible packaging. Then it should have large enough surface to retain the stationary phase as a thin uniform film. Porous supports generally meet these requirements. It should allow the column to have an acceptable pressure drop as regard to mobile phase. It should have sufficient mechanical stability. It must not grind during column packing, impregnation of stationary phase, or regeneration of support material. It should not. When applied to routine analysis or for preparative purposes, it must be relatively cheap, easily available, and permit regeneration. So these are the properties or qualities a liquid must have to act as a solid phase in a liquid chromatography. Okay, so chemically inert, cannot be dissolve or swell, cannot react with the mobile phase, it should be uniform or reproducible packaging, and these are the important things. Mobile phase in liquid column chromatography, it is again one liquid. Solid phase is liquid. Mobile phase is also liquid. So various physical and chemical properties govern the mobile phase. The most important factor is the influence of the mobile phase on the selectivity of the system. The first important one is your selectivity. The solubility of the sample and influence of such property as surface tension and viscosity are important. Solubility of some sample, especially polymer, limits the choice of mobile phase, and use of certain detector imposes constraints. The choice of mobile phase in LC uh, is all important. If water deactivated silica is used as adsorbent, that is the solid phase. The solvent is then varied, giving K prime values in the optimum range, 1 less than K prime less than 10. That is the K value, that is the distribution constant. Solvent strength, which control K prime values of all sample band, is easily predicted in liquid solid column chromatography. It can be defined quantitatively by the solvent strength parameter epsilon O, which are listed for several solvents. Just see this one, these are the several solvents, that is solvent strength and polarity data. The solvent, this is the solubility parameter delta, solvent strength epsilon 0, again the same thing. So if it is N-pentane, the solubility parameter is 7.1 and solvent strength is 0. If it is ethylene dichloride, this is 9.7 and 0.44. That means the solvent strength, it is a important parameter as well as the solubility parameter. Okay. So while considering the choice of mobile phase in NLC, some basic characteristics must be considered. The mobile phase must be immiscible with the stationary phase. Very important. The mobile phase must be immiscible with the stationary phase. And here, just remember the stationary phase is also liquid. It should have viscosity as low as possible for higher column permeability or efficiency. Should have low viscosity. The detector can also limit the phase which can be used. Example, strongly UV absorbing solvent should be avoided with an UV photometric detector. The cost, toxicity, purity and stability of the solvent should be taken into account. What is the cost, whether it is economic or not, toxicity, whether it is toxic, corrosive or not, its purity is very important, it should be it should be in the purest form, and the stability. Stability means it cannot react with the stationary phase. Most important is the selectivity of the liquid-liquid system for a given sample. In liquid-liquid column chromatography, the distribution constant value of the solute are generally controlled by changing the mobile phase. It happens, this distribution constant will change by changing the mobile phase. The scale of solvent polarity, because K is concentration in the mobile phase divided by concentration in the solid phase. And that's why if we changing the mobile phase, the K prime or the distribution constant value will change. The scale of solvent polarity is defined by the Hildebrand solubility parameter delta. Here it is written. This parameter is a good measure of what is commonly called polarity. So this is directly related to your polarity. Polarity means it is the ionic concept, that is the charge. It is the polarity. Non-polar solvent have lower value of delta, while high polar solvents have higher value of delta. So these are the solubility parameter, means this is the depends on the polarity. Pentane is almost a neutral compound, that way this is a non-polar compound, that is this is a organic solvent. The solubility parameter 7.1, while the ethylene dichloride, it is a polar compound, polar organic solvent, so its solubility parameter is 9.7. Triethylamine, this is a non-polar, that's why 7.5. Similarly, benzene also, as the there are 6 carbon 6 hydrogen in cyclic, so this is 9.2 and 0.0 and so on. So this is depend on its polarity, uh, that is the solubility parameter. Then we have the last part, that is development techniques. After having learned about the mobile and stationary phase, it is important to know how the column is developed, how we can develop the column. There are three basic methods: frontal analysis, displacement development, and illusion analysis. Then in the frontal analysis, we have a large sample this large sample in a suitable solvent is passed through a short adsorption column previously saturated with solvent, and the effluent is analyzed continuously until its composition is identical with that of original sample. Let us consider a three component mixture containing equal quantities of each component fed continuously in a column. Because of the force between solute and stationary phase, each solute will be retained to a different extent as it comes into equilibrium with the stationary phase while passing through the column. The first component to elute will be that which is held least strongly in the stationary phase, then the second, and followed by the third. That means frontal analysis means it is the interaction of the solute, that is the component, with the stationary phase. If the in a general concept, if the solute is a polar solute, then it will have higher interaction with the solid phase, so that's why it will separated at the end. And if it is a non-polar component, then this will be separated first. Okay, so the interaction or attachment to the stationary phase depends on the polarity of the component. Just I read this one. The most strongly held of the three will elute in conjunction with the first and second component. Subsequently, there will be no change in concentration of the solute in the mobile phase. There will be no change in concentration of the solute in the mobile phase and the concentration of the respective solute will be the same as the feed mixture. The concentration profile resulting from frontal analysis shown in 5.2a. Just wait, I will. This is 5.2a. Now, this is the plot, that is concentration of the solute versus A. So here what happened? The A is separated. Okay. Then this is the A, again this is the B, and last one is the C. So just here one is the illusion curve for A alone. This is the illusion curve of A. Second one is, this is the second one. This is the illusion curve of the B. And the third one is the illusion curve of the C. That means C is maximum, having maximum polarity, and A is having the least polarity. So which one is the least polar? It will be separated first, and which one having the highest polarity will be separated last. Okay. So then we have the frontal analysis will employ as a development procedure in the early stage of chromatography and before detection procedure are fully effective. It is not often used today and certainly not for quantitative analysis. The reason of this is the no individual component is completely separated from the other in the mixture. So this is this there will be no 100% separation of an individual component from the mixture was observed. Displacement development. Displacement development has the advantage of being able to accommodate large sample and giving sharp separation. It depends on the competition between solute for the active site of the adsorbent and is only really effective in separating very strongly adsorbed material. In displacement development, all the substances in the sample will be held on the stationary phase so strongly that they cannot be eluted by the mobile phase. Okay, so the substances will be strongly held with the stationary phase, and cannot be eluted by the mobile phase or the solvent we have added. They can nevertheless be displaced by substances that are held on the surface by stronger forces with the stationary phase. However, there will be competition between individual solute by and when the sample is placed on the column, the immediately available active sites of the adsorbent will be occupied by the most strongly held component. That means here the components are strongly held to the stationary phase, and when the mobile phase is applied, the immediately available active sites of the adsorbent will be occupied by the most strongly held components. That means the component with higher polarity will strongly occupy the active site of the adsorbent. That is the stationary phase. As the band of the sample moves down the column, the next available site will be occupied by the next strongly retained component. Thus, all the components array themselves along the column in order to their adsorption strength to develop the chromatogram. Another substance known as displacer is introduced into the mobile phase. The displacer has an even higher affinity for the adsorbent than any of the component of the separator. So to give different opportunities to the different components to adhere to the surface of the adsorbent is displacer. The role of the displacer is to displace the one component by the another, and the displacer must have higher affinity to the adsorbent than the other components. Thus, on coming into the contact with the sites occupied by the most strongly adsorbed component, it will displace this component into the mobile phase and thus move on to the next group of site occupied by the next component. That means the less polarity will be replaced by higher polarity, and this process will go on, which will then be itself be displaced. Thus the displacer drives the adsorb component progressively along each column, each component displacing the one in front until they are eluted by the same in the adsorb in the column, the least strongly held being eluted first. This is the primary principle, the least strongly held being eluted first. The concentration profile diagram will be in the 5.2. This is the development stage, the solute concentration versus volume of the mobile phase. So this is the displacer having the highest affinity, and this will displace A, that is having the lowest polarity, followed by B and C. And the last illusion analysis. Illusion means this is the mobile phase we have added to the stationary phase. That is the liquid solvent we have added at the last step of the chromatography. The illusion analysis is the most common technique in chromatography. Employing illusion analysis, complete separation can be achieved. This technique is being widely used for quantitative analysis. A relatively inert solvent is used in large quantities to transfer the component down the column. The nature of the solvent influence the equilibrium between stationary and mobile phase. Nature of the solvent, there are what type of solvent, that is a mobile phase we used. Okay, the nature of the solvent can also affect the shape of the distribution isotherm. Isotherm means at constant temperature the effect analyzed is known as isotherm. Band that might travel down the column with a symmetrical concentration profile in 5.2 C. Just see this one. This is the component AB, and when we inject the solvent, this is the illusion analysis. What happened? The the component gets dissolved in the solvent, and they will move on the basis of their polarity. The higher is the polarity, this will be separated at the end, and lower is the polarity, that is B having lowest polarity between A and B, so B will separate first. Then with one solvent might be in unsymmetrical when illusion analysis used to separate material with widely differing distribution coefficient. So this distribution coefficient depends on the attachment of the component to the solid phase, and this depends on the polarity of the component. The use of single illusion solvent is not practical if the eluent chosen is strong enough to remove the most strongly held material in a reasonable time. It will carry the more weakly held material through the column too rapidly. Okay, if the eluent chosen, that is the solvent chosen, is strong enough to remove the most strongly held material, that between A and B, A is strongly held, and if the solvent is strong enough to remove the component A, okay, remove the component A in a reasonable time, it will carry the more weakly held material through the column too rapidly. That means which is held lightly, that is less polar component will be separated very rapidly. On the other hand, if eluent is weak, solvent is weak, it is very difficult to separate the elute more strongly held material. That means A will be separated very difficult. It is very difficult to separate the component A if the elute is weak. That we have to use, or we have to apply, we have to add the solvent or the eluent which is more stronger than the component which is strongly held with the stationary phase. Therefore, when the sample component have a wide range of distribution coefficient, graded eluents are used. When utilizing graded eluents, the usual procedure is to begin with the weakest solvent capable of eluting one of the sample component and to change increasingly stronger solvent until all of the sample has been eluted. That, that means the addition of the eluent is a continuous process. Still, all the components are separated. And also, if let us consider there are two components in a mixture, and we continuously add 1% of hexane ether solvent, and if it is not separating, then we have to add 2%. Then after, if it is 2% is not effective, then we may go for 5%, and this process will repeat by increasing the percentage of the eluent. The change from one member of the series to the another is made by stepwise increase in concentration of the stronger. This is very important. Stepwise increase in concentration of the stronger solvent. That means if I know what is the strength or the concentration at which the components are separated easily, this will be my optimum concentration, and the concentration I will reach this concentration by stepwise manner. That means I have to use only hexane 0%, then 1% hexane plus ether, 2% hexane plus ether, and so on. And I will see at what concentration the component gets separated easily, and that will be my optimum concentration. And this technique is also known as gradient illusion analysis, because grade by grade we have to change the concentration. The gradient illusion technique can be used not only with mixed solvent but also with any phenomena that will give a solvent gradient in the column. Or example, pH or ionic strength. Okay, in pH analysis also the concentration depends, and also in the ionic strength measurement. Then we have the last part, basic aspects of high performance liquid chromatography, HPLC. This was developed in 1966. The current practice of HPLC is based on application of the pressure to liquid system. HPLC is characterized by a long, narrow column packed with very fine powder with spherical particles, operated at high liquid pressure and possessing a continuous monitoring facility for the common influence. That means it is just the advanced version of your liquid chromatography, where this is high performance. How this liquid chromatography give high performance due to its specificity or the constituents, like the stationary phase we will take here, that is a fine powder with spherical particles, and there will be a narrow column packed, okay, and possessing a continuous monitoring facility for the common effluent. Such chromatographs may be quite expensive, but in turn possible to achieve efficiencies comparable with those obtained from gas chromatography, with separating time of the same order and the ability to work with non-volatile materials. Technically, the development work of HPLC has concentrated on the production of pulse-free pump for generating high pressure. Then in HPLC, the quantitative measurements are readily carried out on the chromatogram, since the amount of substance present is proportional to peak area. What are the advantages? Non-volatile material can be handled in HPLC. Ability to operate long columns at near optimum solvent velocity throughout their length. The nature of mobile phases can be varied to produce either stepwise or gradient illusion on or both. This technique is also detailed in Unit 8. Another in Unit 8, you have the detail about HPLC. Okay, so these are the applications, that is sample separation, what are the stationary phase, mobile phase, and column parameter. So these are the separating samples, steroids, and this is the stationary phase, 1% beta, beta dash, oxy, dipropionitrile on GPAX. Heptane is the mobile phase, and just you have to remember one to two things. Okay, at the end, this unit we have discussed is consist of containing your liquid column chromatography, that is two types, liquid solid chromatography and liquid liquid chromatography, which is an effective tool uh, with respect to your GSC and GLC, gas solid chromatography and gas liquid chromatography. Then on the basis of the type of adsorbent, type of eluent, and type of column we use, the separation techniques becomes more effective. The different components of the modern liquid chromatographic setup has been discussed, and we also discussed the instrumentation part in for your LC. Since the success of the chromatography separation depends on the choice of stationary phase and mobile phase, the criteria used for their selection have been elaborated. So this is all about your LC, and in the next class we will have the next part, that is your unit for unit 6. This is planar chromatography. So in planar means it is paper chromatography. We have TLC, thin layer chromatography, the same thing which we have discussed in our previous class, today's class. This is thin layer chromatography. What are the stationary and mobile phases? What are the apparatus required? And there is also high performance thin layer chromatography, HPTLC, and we have planar chromatography versus TLC quantitative approach, then comparison of this. Then after this, uh, we have we will have block 3. Again, the chromatography, gas chromatography is another chapter. Then we have high performance liquid chromatography, which we have shortly discussed today, that is HPLC. This is unit 8, and after that I think the chromatography part ends. In unit 4 we have ion exchange chromatography also there, and the last one will be size exclusion chromatography, that is depends on the size of the adsorbate, that is silica gel or alumina. Then which is followed by the last unit, will be your electrophoresis and your membrane separation. Membrane separation, and the last one will be your electrophoresis. That is electromigration. This is another separation technique. Okay, so we have also paper chromatography, then column chromatography discussed today, then factors affecting column chromatography, illusion techniques, number of theoretical plates, already n equal to L by H, a number of plates. Then adsorption chromatography, we have this is a column chromatography. Then this is a partition chromatography, bond phase chromatography, partition chromatography, gel permeation chromatography. This is size exclusion, molecular sieve, gel filtration, gel chromatography. These are the stationary phase, GPC, affinity, ion exchange chromatography. This is one unit, ion exchange chromatography. Then we have HPLC. This is unit 8, high performance liquid chromatography. Then we have HPLC detectors. This is one example of chromatogram. This is LCMS, liquid chromatography mass spectroscopy. This is the instrument. We have triple C. This is not in your syllabus. Then we have gas chromatography. This is another unit. Here carrier gas, flow controller, sample injector, column. We have detector and recorder. Without chromatography separation, it is impossible to analyze complex sample by using mass spectroscopy. So thank you for today's class, and if you have any doubt or anything else to ask in today's class within 5 to 10 minutes, and the next class we will have the next class we will have 1 2 3 4. That means the next 4 days we have 4 classes, and within that 4 classes we have to complete these things, and you just have to go through these things very minutely, and you will face, I think, there will be 100-mark paper for your theory paper, which is 3-hour examination, and you will write 10 questions carrying 10 mark each, and you will have 14 questions in total in your question paper. Out of 14 you will write 10 questions. Okay, so this much is from my side from today's class, and anyone having any doubt or anything else related to your program, or anything you would like to share or ask, you may. Over to you guys. Okay,
Hello, sir.
so just go through these PDFs, and at the end of this paper, I will share my PPTs with you, and anyone from you may create one WhatsApp group. Okay, so this is the platform from where we may collect the mobile WhatsApp numbers from different students, and anyone from you may create one WhatsApp group, that is PGDSC program WhatsApp group, and in that group the related PDFs or PPTs we will share, and we will have also discussion on different experiments or practicals, and it is better, I think, from one suggestion from my side, to create one WhatsApp group, which is very much helpful
Hello,
to you and to us also, to conduct this program smoothly for this year.
sir. Already. Hello,
Who will take the charge to create the WhatsApp group? Anyone?
hello,
Or it is already there?
hello.
Mahendra sir, yes. Okay, if it is already there, you should add the tutors who are taking your classes, and that is from Mona Lisa Mahapatra madam took your classes MCH-003 paper, and myself, and also Dr. Rajesh from for your MCH-001 paper. Okay, and so you should add our numbers to that group so that we can contribute or share the slides or PPTs for your better performance in your examination, because as far I know, for the last 2 to 3 years or before that also, the PGDSC result was not good, and the students are not attending the practical examinations by with repeated emails or messages from RC Bhubaneswar, which I faced last year, that out of 90 or 95 students, only 20 to 30 students opt for your experimental part, that is a practical part. Okay, so it is better to have a WhatsApp group to communicate all in one forum, and this will be not mm, yeah, this will be not this will be helpful to everyone to conduct all the parts of this program.
Hello, sir. Hello.
So if so who is the
Hello.
admin of this group? That is your
Hello.
Rohini. You want your voice is not audible.
Hello, sir.
No, your voice is not audible. Rohini is. So the who is the admin?
Hello. Hello.
Sorry. Am I audible?
Hello. Hello, sir. Hello.
Okay. So Abrar Ahmed, you are the admin of this WhatsApp group.
Yes,
Actually,
sir.
no one. My mic is okay. Wait.
Hello, sir.
My voice
Hello.
is audible.
Yes, sir.
Yes, sir.
Just wait. I
Hello.
am just um,
Hello.
existing from this group, and after that I will join again. Just wait, student. Huh. Rohini.
Hello, sir.
Not, not
Hello. Hello. Sir, is am I audible? Hello. Sir, hello. Sir, hello.